Thank you for the warm welcome. Hi, everyone. My name is Lisa. I'm currently a software engineer apprentice at Techtonica. It is a coding bootcamp that focuses on full stack JavaScript. And a unique focus about Techtonica is that their priority is getting women and non-binary people from underrepresented background into tech. And today I'll be talking about hash tables, also known as hash maps or dictionaries in other languages, with you all today. And it was something that I presented with a group in my cohort, a few other people from my cohort to the rest of the program. And I'm excited to share this all with you today. So let's jump right in. So today I'll go over what a hash table is, how it works. So talk about that in a high level, and a couple of key concepts, including hash functions and collisions and how to handle that, as well as the runtime complexity of some of the methods. So what is a hash table? It is a data structure to store key value pairs. So this makes it really good for finding values, adding new values, and removing values. So a hash table is usually like an array with different indices, and each slot is a bucket where we can store the key value pairs. So for example, if we had, we're storing shapes, so for example, an oval, we would encode that key through a hash function, and it will generate an index, which will let us know which slot, which bucket to put it in. So say it hashes to index 0, we can place it there. And here the value is just something arbitrary, but it is just a way to store key value pairs. And if we were to keep adding onto it, so another example, another shape like rectangle, say it hashes to index 5, and we place it in that bucket, and it has its corresponding value. And another example, we'll put in triangle, say it hashes to index 6, and then will be placed in that slot. So how does it know which slot to go? And that's determined with something called a hash function. So what it does, it takes the key, runs it through, and converts it to an integer. And that's the index that it gets assigned to. That'll then be stored in that hash table. And what makes a good hash function is one that would uniformly distribute these keys across the array. And the key should always map to the same integer. So if I give it a certain key, I always expect the same integer output. But in the case where they do end up being assigned to the same index, we have to have a way to handle that. And when they do end up in the same index, that is called a collision. And while there are a couple different ways we can handle that, the example I'll be talking about is called separate chaining. And that is a way where when something gets added into the same bucket, we'll chain them together in a linked list. So see how that looks. Here's an example similar to the one earlier, where we have a key value pair stored at index 0. And say we add another shape, and it happens to also hash it to index 0. What we would do is we would add that key value pair into this linked list that is in index 0. And what makes hash tables really good is that to add, delete, and search, their runtime is O(1) or constant time. They average to that because generally if you have a good hash function, these key value pairs would be uniformly distributed across the array. So adding and deleting and searching would be really quick. And in the worst case, if everything happens to be chained or hashed into the same index, the worst runtime would be O of n, which is linear time, because we would have to just go through the entire linked list. But otherwise, generally, this is a really good data structure to just for these methods because of how quick it is. So to summarize what we talked about today, we learned that hash tables are a data structure to store key value pairs, and how it works is that it runs the key through a hash function, which then uniformly distributes them across. And then in the case where they are hashed into the same index, there is a collision, and we can handle that with separate chaining, for example. And the runtime complexity are generally of 1 or constant time, which makes it a really effective data structure. That's all I have for today. Thank you all for listening, and happy to connect with you all afterwards.